Welcome back. This is our 6th video on SPSS and regression, and our second one related to dummy coding. In our last video, we focused on dummy codes for one variable when we had two categories, and we changed and manipulated data through our data transformations, and created two new categorical variables for Ford and Dodge, and that is related in this case to Chevrolet. If that does not make sense to you, you need to go watch the previous video. So now we're going to extend our model. Previously, we just ran our model using Ford and Dodge variables that we created as predictors to see if there was difference amongst those variables. Now we're going to add a little bit more complexity to our model. We're going to take our original model, which was miles per gallon predicted by horsepower, and we're going to leave that as block 1. So now we have model 1, block 1. We'll just have a very simple regression. And that will take and create block 2, which we're going to add our categorical predictors in. So we've created 0-1 codes for Ford and Dodge. We have our baseline of Chevrolet. Now we're going to say we have two models. When we do our R-squared comparison, we've done this before in the past, statistics, R-squared, continue. When we do this comparison, is model 2 significantly different than model 1? We'll go ahead and click OK. Is there an improvement? Is there an R-squared change is significant and meaningful? That's what we're hoping for. We go ahead and click OK. And we can see Model 1 just has horsepower. Model 2 adds the addition of Dodge and Ford, those categorical variables, those dummy-coded variables into the model. We have all three effectively, including Chevrolet, in our model. Our first R-squared value is 0.36. Our second one is 0.59. Relatively large difference. We can see that R-squared change is significant. So going from the simple regression of horsepower to the multiple regression of horsepower with our dummy codes for our two dummy coded variables of Dodge and Ford coded as 1, we have a significant change. The overall change here, our significance level, is related to that R-squared value overall. And so just to recap that, we can see R-squared change of 15.9. R-squared change is related to an F of 15.9, same here. This 7.3, this F change, is related to this R-squared change R-squared, whereas this 12.6 is related to the 0.59 R-squared. If you need to, pause and listen to that again. Coefficients have been laid out. We see there's a significant predictor for horsepower in the first model. In the second model, all three are significant predictors. We can see their t-values. We have their standardized coefficients and their unstandardized coefficients. If we wanted to, we could take these unstandardized coefficients and we could put them into a model. If we did our prediction model, we would say we have a constant plus some value, whatever horsepower value we have, times our coefficient, our standardized coefficient, and then we would have these Ford and Dodge as kind of turn off and on switches. We would have them in our model, and there is if you have Ford, you have a negative 5.67 impact on your miles per gallon. If you set that to 0 and you set Dodge to 1, then you have a negative 7-point impact on your model. If you set both of those to 0, Chevrolet is significantly lower has a significantly higher overall miles per gallon. It will have an average of 32, whereas we take that baseline, subtract 5.5 from that for Ford, and we subtract 7 from that for Dodge. So in this case, we can see that Chevy has the best horsepower. That's kind of like an analysis of variance. As a matter of fact, we can do things with this that are very much analysis of variance. Before we do that, we're just going to come back and sort of reset and look at our basic interaction effects. Let's go to Analyze, and Regression, and Linear. If we wanted to, we have in our model, if we wanted to put miles per gallon as our predictor and horsepower in our model. Previously, we had done type all set in one block. We could add type here. But now we would like to create interaction. We'd like to see if there's an interaction between vehicle type and horsepower. Well, we actually don't have that variable yet, so I'll go ahead and run this model. This is just a blocking variable. We've sort of seen this blocking before, but now we have block 1. We've seen that block before. We have block 2, which is type, vehicle. In our previous video, we looked at those. But we did not have a covariate. So what I'm going to have to do is manually create a covariate. I'm going to do that. Under transform, I'm going to select compute. I'm going to call this, let's see, we're going to take horsepower and type. I'm just giving it a target name. I'm going to take horsepower and multiply that by vehicle type. Now we could do this with continuous measures. We can do this with categorical measures. In this case, I'm using it with a continuous bicategorical measure, a very simple interaction effect. I'm going to click OK, and we'll go see what it created for us. It created a value that has a 0 for any of our analyses, which are not coded 1. So this is going to be 0 in this case. Remember, from your previous videos, is coded is our cars, our automobiles, and 1 is our trucks. So the interaction, everything is multiplied together. Our type is going to be 0 times any value is 0. 1 times any value is going to be that initial value. So we have actual values for horsepower. We create an interaction variable. In order to run this model, I want to make sure actually to turn off my filter. I believe my filter is still on. Yep. So my filter is still on. I'm going to go to data. I'm going to select cases, and I want to select all cases. In this case, I'm not just selecting and analyzing 3 different manufacturer types. I'm taking type of vehicle, whether it's a car or a truck, and running it in my analysis and using that interaction with horsepower. Let's go ahead and see what that looks like. So linear model, miles per gallon is my outcome. Vehicle type is horsepower is in block 1. Vehicle type is in block 2. And in block 3, I'm going to add that interaction effect. This interaction effect is just horsepower by type of vehicle. So we're going to see whether or not there's a significant interaction above and beyond the effect of the other variables. Since I've already run these blocks, I could have put vehicle type and horsepower in the same block. For me, it'd be interesting to see it as a class example, staging it out for you. And this time I'll go ahead and click R² change and click continue. And I'll click OK. Now we have Model 1 is just horsepower, Model 2 includes horsepower with vehicle type, and Model 3 includes that interaction effect. What we see is that the interaction effect, overall R² change, what it adds to the model is not significant. When we look at the coefficients for that final model, we see, not surprisingly, that coefficient is not significant. So we probably would select Model 2, we would say that the interaction effect is not significant. For now, because we're using dummy coding variables, we're not doing any centering. Centering will be a topic. We can discuss it at a later date. But centering, basically, of our variables has not been done. When you have continuous measures that you're doing interaction effects for, sometimes it's worth centering them around 0, around their mean, in order to remove some of the collinearity that may be occurring in this model. If I go in and analyze this data, I could, under Analyze, General Linear Model, select Univariate, and put miles per gallon in as our predicted variable, or dependent variable. Our fixed factor is vehicle type. Our covariate is horsepower. This will just be analogous in some ways, doing analysis of variance, t-test, but also since we have a covariate, it's like analysis of covariance. You can do all of your regression models in the univariate general linear models framework. We've talked a lot in class how these are the same. We've demonstrated this previously, but just as an example, we'll have to toggle this around to get a true interaction effect, but we'll see we can get the main effects to start. I run this, I get an overall R squared of 0.699, which is what we got in our regression model for this model. And we see that we have an FA of 175. If I just use those two variables in the model, which I believe I did in this one, we see that we have, I didn't do R squared change for that one. We see that in model 2, which just had those two main effects, we have 175, and we have an R squared of 0.69. Now, that would just be using these as main effects. If we wanted to include the interaction effect, we go analyze, general linear model univariate. You have control over these models. I'm going to go to model feature, and I can determine, I can build which terms I want in my model. Well, if I want main effects in the model, I can select both of these and create main effects in the model. And then I could create also an interaction term. So I have to specify that. We're using type 3 sums of squares. I'm not going to get into those right now. Analysis of variance, often we change these, we can potentially change these around, and we're going to include our intercept in the model. That would be from your previous coursework, so we're not going to do that now. And I will go ahead and click OK. And we can see that type by horsepower is not significant in our model. Our significance for type and horsepower and our overall R squared value is 0.699. This is like the third model that we ran that was not significant. So that's just to give you kind of a quick, peek at running analysis of variance or technical, or also analysis of covariance analogous to our regression models. Remember, regression and analysis of variance are the same thing mathematically. We just frame them out differently. So in order to tease out analysis of variance out of regression, we do some dummy coding or other types of coding in our model. And just one last example that we'll use. I'm going to go ahead and turn back on our filter. Probably unnecessary since some of it's missing, but for now, I'll turn back on our filter. Click OK. And I'll run several analyses here. I'll run our regression model. We used miles per gallon. And we used Ford and Dodge to see if there was a difference amongst these three variables. And previously we saw there was. We see that we have a 303 R squared, a significant value here as well. Then we can analyze this under the general linear model framework. Our miles per gallon, and we could take Ford and Dodge, and actually let me only do main effects for now. Click continue, click OK. We get 0.303, the same R squared value, we get the same F value. We can see that the coefficients here are each one of these Ford and Dodge, the main effects are significant. We could also analyze this in sort of a more old-fashioned way for us. From an analysis of variance perspective, we could take the subset of manufacturer, which has all three of those variables coded, and our model, we'll just use the full model, click continue, click OK. And we see again, we have a 0.303, we have a 5.8 F value, and that is significant. So whether we're doing this in the R framework, whether we're dummy coding and doing it in kind of a generalized framework, or whether we're doing an analysis of variance framework, all three pretty much end up with the same results. We see in our R framework that the coefficients, those T values are both significant, T for Ford, T for Dodge. And if we were to go down here, 0.028 and 0.022, the coefficients here in the R framework, multiple regression framework, are the same as the significance levels here because T squared equals F, right? That we could go back and you could do those calculations with your own. I'll just end it with that so that way it kind of wraps up, maybe makes more believable that what we're doing in our R squared, when we're doing multiple regression models, is the same thing we did or you have done in previous courses with analysis of variance and that we've done in this course. And those are some more of the relationships.